Welcome back. In my previous video, I had seen zeros of analytic function. The idea of zeros of analytic function: either fz is identically 0 or fz not identically 0. When fz is identically 0, that means every point in this neighborhood is a 0 or zeros are always isolated. Today's goal of this lecture, today at first I will see what is the uniqueness theorem or identity theorem. The statement of uniqueness theorem is: suppose f is analytic in a domain D where D is obviously open and connected, then the set of 0 f in the domain has a limit point z star in D, then f is identically 0 in this domain. That means, first, if f is analytic, second, D is open plus connected domain, third, zeros has a limit point, and obviously this limit point belongs to this domain. Then we can tell, obviously, f is identically 0 in this domain D. This is the uniqueness theorem. At first, I will see one example. Next example, fx equal to e to the power minus 1 over x when x greater than equal to 0 and 0 when x less than 0. Notice, for x not equal to 0, all derivative of fx is equal to 0. That means fn x is equal to 0 when x less than equal to 0. And we all of us know each point of negative real axis is a limit point which belongs to the set. Then, by uniqueness theorem, we can tell the function fx is identically 0. But this is not true. Why? Because the uniqueness theorem does not hold for R. So, we cannot tell the function fx is identically 0. All property of uniqueness theorem has satisfied here. But since uniqueness theorem does not hold for real line, so we cannot tell the function is identically 0. Okay? Well, means uniqueness theorem only applicable in complex, not applicable in real. Another approach of uniqueness theorem is, suppose fz is analytic in the domain D and zn is a sequence of distinct points who is converging to z0 in the domain D. That means, if fzn equal to 0 for each n, Since Zn is a sequence of distinct points which is converging to Z0, that means Zn converging to Z0. If fZn is 0 for each n, then by identical or uniqueness theorem, we can tell fz is identically 0 throughout the domain. That means actual idea is, first, fz is analytic. Second, the domain is open connected. Third, there exists sequence Zn which is converging to Z0, and obviously this Z0 belongs to this domain. Then by identity theorem or uniqueness theorem, we can tell fz is identically 0 throughout the domain, throughout the domain D. Okay? Approach of uniqueness theorem. If an analytic function have infinite zero in a domain such that set of zeros has a limit point in this domain, then fz is identically 0. That means if we consider s equal to z1, z2, z3, so on, if fzi is 0 on the set S, but these zeros has a limit point in the domain D, has limit point in D, then we can tell fz is identically equal to 0. Whole fz is identically equal to 0 whole D. I hope my all viewers have understood three approach of uniqueness theorem. If fzi, where zi is the zeros of this function, if fzi is equal to 0 on the set S, but these zeros has a limit point in the domain D, S is the subset of domain D, then we can tell fz is identically 0 on whole D. Okay? First example, fz equal to e to the power 1 over 1 minus z minus 1 in the domain mod z less than equal to 1. For this, at first consider how look like the zeros. Here e to the power 1 over 1 minus z minus 1 equal to 0, that means that imply e to the power 1 over 1 minus z equal to e to the power 2 pi ni. That imply 1 minus z equal to 1 over 2 pi ni. That imply z equal to 1 minus 1 over 2 pi ni. We can write this as Zn equal to 1 minus 1 over 2 pi ni. We can consider this sequence, and this sequence Zn converging to 1. But here the domain is mod z less than 1, not included the boundary. So, here by uniqueness theorem we cannot tell fz is identically 0 on throughout the domain, because limit point lies on the boundary. It is not true, because by uniqueness theorem limit point lies must be inside the domain. Since limit point lies on the boundary, so fz not identically equal to 0 throughout the domain. I hope my all viewers have understood this is okay. My next equal to set of those z's such that 1 less than equal to z less than equal to 3. That means this z, here mod z equal to 1 and here mod z equal to 3, that means this domain. Here the function is defined as f from d to complex number such that f of z equal to 0 for mod z less than 1 and f of z equal to 2 for mod z greater than 3. Notice here f is analytic in D and the set of 0 of the function f is s equal to z such that modulus of z less than 1. In this set, function has limit point. But by uniqueness theorem, we cannot tell f is identically equal to 0 because here given domain D is not connected. Just recall, at first domain would be connected, then analytic. Then if the zeros has a limit point which belongs to in the set, then we can tell the function is identically equal to 0. Next example, fz equal to sine 1 over z. On the domain, here the domain is mod z less than equal to 1. Sine 1 over z equal to 0 means 1 over z equal to n pi, that implies z equal to 1 over n pi. Consider zn equal to this sequence 1 over n pi, where zn tends to 0. Obviously, this limit inside this domain, but is the function is identically equal to 0? By uniqueness theorem, no. Why? Because the function is analytic whole domain, but not analytic at the point 0. So the function is not identically 0. In this consequence of uniqueness theorem or identity theorem is, let G be a region and suppose that f and g are analytic on the set G, and suppose fz equal to gz, and this is true for all z in S, where S is a subset of G. If S has a limit point in the set G, where G is main domain, here G and here S, then we can tell by identity theorem, since S has a limit point in G, so by identity theorem we can tell fz equal to gz on the set C. Okay? Actually, the consequence is, suppose that f and g are analytic in a domain D, and if S is set of 0 of f minus g in D has a limit point z star in D, then we can tell fz equal to gz is identical in the domain D. That means actual idea is, consider Az equal to fz minus gz for all z belongs to S. Since fz and gz is analytic, that means their difference also would be analytic, that means S is analytic in S. And if S has limit point in the domain D, then we can tell f and g is actually identical, and this is identical in whole domain. I hope my all viewers have understood. That means first f and g are analytic. then their difference hz equal to fz minus gz are analytic. Analytic on the set S. If AZ has a limit in D, then we can tell FZ and ZZ are actually identical in whole domain D. And sequentially we can tell, suppose Zn is a sequence of points having limit point in a domain D. Suppose Zn converges to Z0 where D is open connected set. If Fz and Gz are analytic in the domain D, since Zn converges to Z0, therefore Fzn equal to Gzn, and this is true for Ezen. And since Zn converges to Z0, therefore that implies Fz0 equal to Gz0 for Ezen. Therefore actually Fz equal to Gz throughout the domain D. This is the identity theorem. Next, second identity theorem. Similar to before, I will see some example of this identity theorem or uniqueness theorem. First example, f defined from complex number to complex number be an entire function with f of 1 over n equal to 1 over n square, and this is true for all n belongs to natural number. Then which of the following is true? Option 1, no such f exists. Option 2, such of f is not unique. Option 3, fz equal to z square, and this is true for all z belongs to complex number. Option 4, f need not be polynomial function. For this, I will apply the second identity theorem. Here given f of 1 over n equal to 1 over n square, and consider gz equal to z square. And obviously g1 by n equal to 1 over n square. Now consider the set S equal to 1 over n such that f of 1 over n equal to 1 over n square. Obviously this 1 over n goes to 0. So that means 1 over n goes to 0, which is belongs to C. Therefore by identity theorem we can tell fz equal to zz, and zz equal to z square. So fz equal to zz, and this is true for all complex number, because here fz equal to zz in the set S, and by identity theorem, since limit point the sequence converges to the limit, those limit point, and this limit point belongs to the domain, so we can extend it, this set, on the whole complex plane, because this set is actually the set where fz equal to zz, and here by identity theorem we can extend this set in whole complex plane. I hope my all viewers have understood this is. Next example. Second example, similar to before, fz is analytic and mod z less than 1. Then which of the following are true? Option 1, for all n belongs to natural number, we have f of 1 over n equal to 1 over n square. Then that imply fz equal to z square. Here also I will use the identity theorem. Similar to before, similar example. F of 1 over n equal to 1 over n square. And consider new function z equal to z square. And consider hz equal to f of z minus z of z. Then h of 1 over n equal to f of 1 over n minus g of 1 over n, and 1 over n, and g of 1 over n means this is f of 1 over n, and g of 1 over n means 1 over n square. So this value is obviously 1 over n square minus 1 over n square. So this value is obviously 0. So h of z is identically 0. That means f of z equal to c of z. True. The set is where 1 over n such that f of z equal to c of z, and 1 over n since goes to 0. So by extension theorem we can extend f of z equal to z of z on whole complex number. Similar to before, next example, for all n belongs to natural number, f of 1 minus 1 over n equal to 1 minus 1 over n square. Consider here g of z equal to z square, and given f of 1 minus 1 over n equal to 1 minus 1 over n square. This is given, and this is I have considered this is zz. This is new function. Then consider hz equal to f of z minus z of z. Then h of 1 minus 1 over n equal to f of 1 minus 1 over n minus g of 1 minus 1 over n. And f of 1 over 1 minus n means 1 minus 1 over n whole square, and g of 1 minus 1 over n means since g of z equal to z square. Now put the value, then this value would be 1 minus 1 over n whole square, and so this value is 0. Since here the limit is 1 which is belongs to complex number, so we can tell hz is identically equal to 0. And if hz is identically equal to 0, that means f of z equal to c of z. If we consider the set s equal to here 1 minus 1 over n such that f of z equal to g of z, since here the limit point of 1 minus 1 over n is in this, for this sequence the limit point is 1. Since limit point belongs to complex number, so we can tell, obviously we can extend it x f of z equal to g of z on whole complex number. I hope my all viewers have understood this. Okay, so option 1 and option 2 is a right option. Both are right. I hope my all viewers have understood identity theorem in better way. In my next video, I will discuss identity theorem, different type of example based on identity theorem. But at first I will highly recommend you please see today's video with pay attention, because if you see this video with pay attention, then you will understand my next video. Okay? See you soon. Stay safe and stay positive always, and don't forget to do subscribe my channel for more videos. Thank you so much.